Consider for a moment the weight of a single breath. The air that now fills your lungs has been breathed before, by philosophers who wondered about the stars, by creatures whose names we have never spoken, by forests that once covered continents long since swallowed by the sea. Every molecule in that breath carries within it a history so vast, so interwoven with the story of the universe itself, that to understand it fully would require a mind capable of holding eternity in a single thought. We are not yet that mind. But we are reaching. Slowly and perfectly, with instruments of glass and mathematics and stubborn curiosity, we have begun to measure the immensity into which we were born, and what we have found there, in that outer dark, in those cold spaces between the burning lights, is something that no ancient dreamer could have prepared us for. The cosmos is not merely large. It is not merely old. It is something for which human language does not yet possess the proper words, and the journey we are about to take together is a journey toward that wordless understanding, toward the horizon where numbers dissolve into all. Begin with the earth itself, because that is the only place any of us has ever stood, and it is therefore the only honest beginning. Beneath your feet, right now, there are approximately 6 sextillion metric tons of rock and iron and nickel and silicate magma, all of it spinning at roughly 1,670 kilometers per hour at the equator, all of it hurtling through space at 107,000 kilometers per hour, as it completes its annual journey around the sun. The planet is, by the standards of human construction, enormous. Its circumference stretches to about 40,075 kilometers, a distance that would take a healthy person walking without rest approximately 334 days to cover. The deepest point in the ocean floor, the Challenger Deep in the Mariana Trench, plunges 10,935 meters below the surface of the sea, a depth at which the pressure exceeds 1,000 times the atmosphere you breathe so effortlessly right now. The highest point on the planet's surface, the summit of Everest, rises 8,849 meters above sea level, a height at which the air thins to a third of its sea level density, where unprotected human tissue begins to fail within minutes. Between that highest peak and that deepest trench lies a vertical span of roughly 20 kilometers, a range that encompasses virtually every living thing that has ever drawn breath on this world. And yet, when placed beside what lies beyond, when held up against the scale of even our nearest celestial neighbors, that entire 20-kilometer envelope of life and geology shrinks to something almost incomprehensibly thin, a membrane, a film of existence on the skin of a pale blue dot drifting in an ocean of darkness. The moon, our nearest neighbor, lies on average about 384,400 kilometers away. That number, 384,400 kilometers, is the kind of figure that the human brain processes abstractly, storing it somewhere near other large but meaningless numbers, the national debt, the number of stars visible to the naked eye, without truly grasping its experiential reality. So let us try to make it real. If you could drive a car at highway speeds, 100 kilometers per hour, directly upward into the sky and keep driving without stopping for food or sleep or fuel, it would take you approximately 160 days to reach the moon. If you were to lay every human being who has ever lived end to end, placing them head to toe in a great chain of human bodies, you would need roughly 380 billion of them to reach from here to there, and we estimate that approximately 108 billion human beings have ever been born on this planet, meaning you would need to use every human who has ever lived not once, but 3.5 times over. The moon is far. We sent astronauts there. 12 men walked on its surface between 1969 and 1972, and the fastest journey any crew made to reach it took about 3 days. 3 days to travel 384,400 kilometers. And yet the moon, which governs our tides and lights our nights, and has been the subject of human poetry and longing since the first creatures with the capacity for wonder gazed upward. The moon is merely the first step in a journey outward that grows, with each step, more difficult to comprehend. Beyond the moon lies the inner solar system, a neighborhood that seems, from the perspective of interstellar distances, almost cozy, but which contains volumes of empty space so vast that if you were to compress the solar system to the scale of a large building, every planet would be invisible to the naked eye, mere specks lost in the corridors of that imaginary structure. The sun, our star, sits at the center of this neighborhood, and it is enormous in a way that demands a moment of quiet reflection. If the sun were hollow, you could fit approximately 1.3 million Earths inside it. Its diameter is 1.39 million kilometers, roughly 109 times the diameter of the Earth. Its surface temperature hovers around 5,500 degrees Celsius, hot enough to vaporize any material known to science. Its core, where the nuclear fusion reactions that power all life on our world are continuously occurring, reaches temperatures of approximately 15 million degrees Celsius, a heat so extreme that the energy produced there takes approximately 100,000 years to work its way outward through the dense plasma of the sun's interior before finally escaping as the sunlight that falls on your face on a summer morning. That light, that warmth you feel on your skin, was generated in the sun's core when our ancestors were still learning the rudiments of stone tools. The sun is profligate with its energy, releasing approximately 3.8 times 10 to the power of 26 watts every second, a figure so large that if you could somehow capture just 1 second of the sun's total energy output, it would power all of human civilization as it currently exists for the next 3.5 million years. The distance from the Earth to the Sun, approximately 150 million kilometers, is a unit of measurement that astronomers call the astronomical unit, or AU, and it serves as a convenient yardstick for measuring distances within our solar system. At this distance, light, traveling at 299,792 kilometers per second, the fastest speed at which anything in this universe can move, takes about 8 minutes and 20 seconds to cross from the Sun to the Earth. 8 minutes. Hold that number. When you look up at the Sun, shielding your eyes against its brightness, you are seeing it not as it is, but as it was 8 minutes and 20 seconds ago. You are looking into the past. This is a simple truth, almost trivially simple in its statement, but it contains within it the seed of a profound philosophical vertigo that deepens with every increase in scale. Every act of looking is an act of looking backward in time. Every photon that strikes your retina carries information not about the present state of its source, but about the state of that source at the moment the photon was emitted. At the scale of everyday life, this temporal displacement is so small as to be irrelevant. The light bouncing off a friend's face has traveled perhaps 2 or 3 meters, and was therefore emitted perhaps 10 nanoseconds ago. But as our gaze reaches outward, as our instruments extend our sight across progressively greater distances, the time delay of light becomes a window into history, and eventually into a past so remote that the objects we observe may no longer exist in the form we see them. Mars, the next planet outward from the Sun, circles at approximately 1.5 astronomical units, meaning that on average it is about 225 million kilometers from Earth, though this distance varies significantly as both planets move in their separate orbits. At closest approach, the two worlds can be as near as 54 million kilometers, while at their most distant, they are separated by more than 400 million kilometers. The light travel time across this average distance is about 12 minutes. When signals from our Mars rovers reach mission control on Earth, those signals, themselves traveling at the speed of light, take anywhere from 3 to 22 minutes to arrive, depending on where the planets are in their orbits. This means that when a rover on Mars encounters an unexpected obstacle or experiences a mechanical failure, the engineers back on Earth cannot respond in real time. They must command the rover based on information that is already many minutes old, then wait an equal amount of time for their commands to arrive, and then wait again for confirmation of the result. It is remote control with a temporal lag measured in the tens of minutes, a constraint that becomes only more severe as we push our probes and spacecraft outward into the solar system. It is the first taste of what genuine interstellar distance would mean for human exploration, a universe in which communication itself is constrained by physics to a pace that no engineering ingenuity can overcome. Jupiter, the largest planet in our solar system, orbits the Sun at a distance of about 5.2 astronomical units, roughly 778 million kilometers. It is a world that beggars description in terrestrial terms. Its diameter at the equator is 142,984 kilometers, approximately 11 times the diameter of Earth. Its mass is 318 times the mass of our planet, and it is so large that if you were to combine all the other planets in the solar system into a single body, that body would still be less than half Jupiter's mass. Its great red spot, a storm that has been raging continuously for at least 350 years, and possibly much longer, is itself larger than the entire Earth, a swirling vortex of clouds and high-pressure winds that contains within it, at any given moment, energies comparable to the largest hurricanes in Earth's history, multiplied 1,000-fold and sustained across centuries. Jupiter has 95 known moons, a miniature solar system in its own right, and among them is Europa, a world approximately the size of our own moon whose icy surface conceals what planetary scientists believe is a liquid water ocean containing more water than all of Earth's oceans combined. Beneath a crust of ice perhaps 10 to 30 kilometers thick, warmed by tidal forces generated by Jupiter's immense gravity, that ocean may have existed for billions of years. Whether it harbors life, whether there are creatures in that dark warm saltwater pressing against the underside of their frozen ceiling and perhaps, in their own alien way, wondering about the universe above them, this is one of the most urgent and electrifying questions in all of contemporary science. Saturn, at 9.5 astronomical units from the Sun, is a world of such surpassing beauty that even photographs taken by our most sophisticated space telescopes, even the direct images captured by the Cassini spacecraft during its 13 years orbiting the planet, cannot quite prepare the mind for the emotional reality of its appearance. Its ring system, extending outward to a distance of 282,000 kilometers from the center of the planet, is composed of billions of individual pieces of ice and rock ranging in size from tiny grains to chunks the size of houses, all of them orbiting Saturn in a plane so flat, the main rings are typically only about 10 to 100 meters thick, despite extending hundreds of thousands of kilometers in width, that the geometry seems almost impossibly precise, as though some vast and patient intelligence had arranged them with a craftsman's care. Saturn itself is the least dense of all the planets, with an average density lower than that of water. Were you to find an ocean large enough to contain it, Saturn would float. Its winds, measured at cloud-top level, exceed 1,800 kilometers per hour at the equator. Its North Pole displays a persistent hexagonal storm formation, a six-sided weather pattern whose individual sides are each longer than the diameter of the Earth, and whose geometric regularity has puzzled scientists since its discovery by the Voyager spacecraft in the 1980s. Beyond Saturn, in the outer reaches of the solar system where sunlight has diminished to a faint and distant gleam, roughly the brightness of a full moon on Earth, lie the worlds of Uranus and Neptune, distant enough that even our fastest spacecraft have reached them only once, briefly, in flyby trajectories that gave us tantalizing glimpses of alien worlds before hurtling onward into the dark. Neptune, the most distant of the 8 recognized planets, orbits at about 30 astronomical units from the Sun, a distance of approximately 4.5 billion kilometers. Light from the Sun takes about 4 hours to reach it. The signals from Voyager 2, which flew past Neptune in 1989 and is now the most distant human-made object to have visited another planet in our solar system, took 4 hours and 6 minutes to reach Earth even after traveling at the speed of light. Voyager 2 itself, moving through space at about 55,000 kilometers per hour, a speed that would take it from New York to Los Angeles in roughly 3 minutes, had been traveling for 12 years when it reached Neptune. 12 years of uninterrupted flight at 55,000 kilometers per hour, and it had crossed just 30 astronomical units. The scale of the solar system, even without considering the vast region beyond the known planets, is already enough to induce a kind of cognitive vertigo. But the solar system does not end at Neptune. Beyond Neptune lies the Kuiper Belt, a region of the solar system extending from about 30 to 50 astronomical units, populated by hundreds of thousands of icy bodies, dwarf planets, including the beloved Pluto, reclassified in 2006, but no less remarkable for its demotion and a frozen remnant of the solar system's formation. Beyond the Kuiper Belt lies the scattered disk, a more distant and dynamically complex region whose outer boundary may extend to hundreds of astronomical units from the Sun. And beyond that, at distances of perhaps 2,000 to 100,000 astronomical units, lies the Oort cloud, a vast spherical halo of cometary nuclei, billions of them, perhaps trillions, orbiting so slowly and so distantly from the Sun that their orbital periods may be measured in millions of years. The Oort cloud has never been directly observed. It is inferred from the orbits of long-period comets that occasionally fall inward toward the Sun, drawn in by some distant gravitational perturbation, a passing star, a giant planet's distant gravitational tug, and their origins in that remote reservoir are traced backward through the mathematics of celestial mechanics. The outer edge of the Oort cloud, if such a boundary could even be said to exist in any meaningful sense, may lie at a distance where the Sun's gravitational influence becomes comparable to the gravitational influences of neighboring stars. This is the edge of the solar system not as a sharp boundary, but as a gradual fading, a dissolving of one gravitational dominance into the vast neutrality of interstellar space. The nearest star to our Sun is Proxima Centauri, a red dwarf star that forms part of the Alpha Centauri triple star system. Its distance from Earth is approximately 4.24 light-years. A light-year, the distance that light travels in 1 year at 299,792 kilometers per second, is approximately 9.46 trillion kilometers, or 9,460 billion kilometers. Multiply that by 4.24, and you arrive at a distance of approximately 40 trillion kilometers, or 40 trillion kilometers. To reach Proxima Centauri with our fastest current spacecraft, Voyager 1, which is moving at approximately 61,000 kilometers per hour, would take about 73,000 years. If humanity had launched such a spacecraft at the dawn of agriculture, at the moment when our ancestors first began to deliberately plant seeds in the soil of the Fertile Crescent, it would still be some 63,000 years away from its destination. The gap between stars is not merely large. It is, by any standard of human temporal experience, essentially infinite. And yet Proxima Centauri is our nearest neighbor. It is, in the context of the galaxy, just next door. Proxima Centauri is known to harbor at least one planet, Proxima b, discovered in 2016 and orbiting within the star's habitable zone, the range of distances from a star at which liquid water could theoretically exist on a planet's surface, assuming the right atmospheric conditions. Proxima b has a minimum mass roughly 1.27 times that of Earth, and it orbits its star every 11.2 Earth days. It is, by any objective measure, one of the most significant discoveries in the history of astronomy, the nearest potentially habitable world beyond our solar system, lying just 4.24 light-years away. Just. The qualifier sits there in that sentence, like a gentle joke, a reminder that even the universe's nearest landmarks are separated from us by gulfs that our engineering has not yet found a way to cross. Several proposals have been put forward for reaching Proxima Centauri on timescales shorter than geological time. The Breakthrough Starshot initiative imagines laser-propelled microchip-sized probes sailing on sails of light, reaching perhaps 20% of the speed of light, and arriving at Proxima Centauri in about 20 years. This is, compared to any other proposed method of interstellar travel, staggeringly fast. And yet even at 20% of light speed, the journey takes 2 decades. And the probes, each smaller than a postage stamp, could carry no human crew, would return no data for 4 years after their arrival, and would have no way to slow down. They would sweep through the Alpha Centauri system in a matter of hours, taking what images and measurements they could in their brief passage, and then continue outward into the interstellar dark forever. A 20-year journey, ending in a few hours of observation. This is the present frontier of human ambition in space exploration, and it serves as a stark illustration of the immensity that separates us from even the nearest stars. The Milky Way galaxy, the vast spiral structure of stars and gas and dust and dark matter within which our solar system resides, contains somewhere between 100 billion and 400 billion stars. The most recent and precise estimates from the Gaia mission, a space observatory that has mapped the positions and movements of nearly 2 billion stars with extraordinary precision, suggest a figure closer to 100 to 400 billion, with the uncertainty reflecting genuine scientific debate about the number of faint red dwarf stars that make up the galaxy's population. Our solar system sits in one of the Milky Way's spiral arms, the Orion Arm, also called the local spur, at a distance of approximately 26,000 light-years from the galactic center. The galaxy itself spans approximately 100,000 light-years from one side to the other, though it is not a simple disk, but a complex and three-dimensional structure with a prominent central bulge, a thin disk of young stars and gas, a thick disk of older stars, and an extended halo of ancient stars and globular clusters that reaches out to perhaps 200,000 light-years from the galactic center. Our solar system completes one orbit around the center of the Milky Way every 225 to 250 million years, a period that geologists call a cosmic year or galactic year, moving at approximately 220 kilometers per second through the galaxy. Since the Earth formed, about 4.54 billion years ago, our solar system has completed roughly 20 orbits of the galactic center. The first orbit began when the Earth was still a molten ball of rock being bombarded by the leftover debris of the solar system's formation. The last full orbit was completed approximately 225 million years ago, at a time when the first dinosaurs were just beginning to appear in the fossil record. To cross the Milky Way from one side to the other at the speed of light would take 100,000 years. A human lifetime of 80 years represents 0.08% of a cosmic year. Every civilization in human history, from the first cities of Mesopotamia to the present day, occupies a span of about 10,000 years, a sliver, a heartbeat, a barely perceptible instant in the life of the galaxy. The galaxy is approximately 13.5 billion years old, meaning that it has been forming stars and building complexity since a time when the universe itself was less than 300 million years old. The oldest stars in the Milky Way are ancient enough that the very concept of life as we understand it, carbon-based, chemistry-driven, metabolically sustained, would have been impossible in their early environment because the heavier elements necessary for life, the carbon and nitrogen and oxygen and iron and calcium and phosphorus, had not yet been created. These elements are themselves the products of stellar evolution, forged in the nuclear furnaces of stars, and scattered across space in the catastrophic deaths of those stars, supernovae and neutron star mergers, and the slow winds of aging red giants. Every atom in your body more complex than hydrogen was created inside a star that lived and died before our sun was born. You are made of star stuff, as the poet-scientist said, and this is not metaphor. It is the most literal and verifiable truth that cosmology has to offer. The center of the Milky Way harbors Sagittarius A*, a supermassive black hole with a mass of approximately 4.1 million times the mass of our Sun. For most of its history, this black hole has been relatively quiet. Astronomers call it quiescent, emitting occasional flares of X-ray and infrared radiation as material occasionally falls into it, but not producing the spectacular jets and luminous accretion disks that characterize the most active galactic nuclei in the universe. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A*, showing the characteristic bright ring of glowing gas surrounding a central dark shadow. The event horizon, the point of no return beyond which not even light can escape. That image, assembled from radio observations taken simultaneously by telescopes distributed across the Earth, used the entire planet as an effective antenna to achieve the resolution necessary to image an object 26,000 light-years away. It is a triumph of human ingenuity, a testament to the collaborative spirit of science, and a humbling reminder that at the heart of our galaxy, in the dense and turbulent neighborhood of the galactic center, there exists an object so extreme in its physics that the very concepts of space and time as we normally understand them break down at its boundary. Beyond the Milky Way, the universe continues. Our galaxy belongs to a small group of galaxies called the Local Group, which contains approximately 54 galaxies of various sizes, dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy, and their respective retinues of satellite galaxies. The Andromeda Galaxy, also known as M31, is the largest galaxy in the Local Group, containing perhaps 1 trillion stars, roughly 2 to 3 times the number in the Milky Way. It lies approximately 2.537 million light-years from Earth, meaning that the light we see when we observe Andromeda left the galaxy about 2.5 million years ago, at a time when our own ancestors, the early hominids of East Africa, were just beginning to make the first rudimentary stone tools and had not yet evolved into anything that could be called human in the modern sense. The Andromeda Galaxy is, at this distance, the most distant object visible to the naked eye under dark skies, appearing as a faint smudge of light about twice the apparent diameter of the full moon. To see it, to pick out that pale elliptical glow in the darkness with nothing more than your own eyes, is to experience directly the temporal depth of the universe, to hold in your vision something that is simultaneously an object and a message from a time before humanity existed. The Andromeda Galaxy and the Milky Way are approaching each other. Gravitational attraction between these two massive systems is drawing them together at approximately 110 kilometers per second, and astronomers calculate that they will begin a slow collision in approximately 4.5 billion years. The word collision is, in this context, profoundly misleading because galaxies are mostly empty space. The actual stars in each galaxy are separated by distances so vast that the probability of two individual stars colliding during a galactic merger is extremely low. What will happen instead, over a time frame of billions of years, is that the two spiral structures will interpenetrate, their stars orbiting wildly in new configurations, gravitational interactions throwing some stars entirely out of both galaxies into intergalactic space, triggering massive waves of star formation as interstellar gas clouds are compressed together, and ultimately settling. After billions of years of tidal interactions and repeated passes, into a single large elliptical galaxy, sometimes called Milkometa by the astronomers who have modeled this future event. The Sun and Earth will almost certainly survive this process, though their positions in the merged galaxy will be very different from their current positions, and the night sky as seen from their future Earth, assuming there is still an Earth and something on it capable of looking up, will be a spectacle of extraordinary and alien beauty. The local group itself is a small eddy in a much larger gravitational structure. It sits at the outer edge of the Virgo supercluster, a collection of galaxy groups and clusters containing perhaps 1,300 individual galaxies distributed to a volume of space about 110 million light-years across. The Virgo supercluster, in turn, is itself merely a lobe of a much larger structure called the Laniakea supercluster, identified in 2014 by a team of astronomers led by Brent Tully using peculiar velocity maps of the local universe. Laniakea, the name comes from the Hawaiian words meaning immeasurable heaven, contains approximately 100,000 galaxies distributed to a volume roughly 520 million light-years in diameter. Its total mass is approximately 10 to the power of 17 solar masses. Within this supercluster, galaxies and galaxy groups are being drawn by gravity toward a massive concentration of mass called the Great Attractor, located approximately 250 million light-years from the Milky Way in the direction of the constellation Centaurus. The Great Attractor is not a single object but a region of space of extraordinary mass density, centered on a concentration of galaxy clusters called the Norma cluster, which itself sits within a larger overdensity called the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. Our galaxy, along with thousands of others in the local group and the Virgo supercluster, is being drawn toward this distant mass concentration in hundreds of kilometers per second, a cosmic river of galaxies flowing toward a gravitational sink so large it shapes the motions of structures across hundreds of millions of light-years. These large-scale structures, the filaments, walls, and voids that make up what cosmologists call the cosmic web, are among the most striking features of the universe on scales above a few hundred million light-years. The universe is not homogeneous at these scales. Galaxies are not distributed randomly through space, but are gathered into clusters and superclusters that themselves form elongated filaments, like threads of a vast three-dimensional web, while between these filaments lie enormous voids, regions of space nearly empty of galaxies, ranging from tens to hundreds of millions of light-years in diameter. The largest known void, the Bode's void, is approximately 330 million light-years across and contains only about 60 known galaxies in a region of space where, based on the average density of the universe, you would expect to find thousands. The origin of the Bode's void is not fully understood, but it is thought to be the result of the gravitational dynamics of the early universe. Regions of slightly lower than average density that have been progressively emptied by the gravitational pull of surrounding denser regions, their galaxies drawn outward into the surrounding filaments over billions of years. The void is not truly empty. It contains dark matter, faint dwarf galaxies, intergalactic gas, but it is emptier than anything in ordinary human experience, a vast and ancient hollow in the fabric of the cosmos. The largest known structure in the observable universe, as of current knowledge, is the Hercules Corona Borealis Great Wall, a massive filamentary structure of galaxy clusters discovered in 2013 and estimated to span approximately 10 billion light-years, or about 1/10 of the diameter of the entire observable universe. Its existence challenges some cosmological models, as standard cosmology predicts that structures larger than about 1.2 billion light-years should not exist. The universe has not been around long enough, and the speed of gravitational interactions is limited by the speed of light, so structures larger than a certain scale cannot have formed through gravitational attraction alone in the time available. The Hercules Corona Borealis Great Wall, if its dimensions are confirmed, may require revisions to our understanding of how large-scale structures form, or may reflect subtle aspects of the initial conditions of the universe's expansion that we do not yet fully understand. Science does not fear such anomalies. On the contrary, they are its food. Every observation that challenges a model is an invitation to think more carefully, to look more deeply, to construct a better and more accurate picture of reality. The observable universe, the region of the universe from which light has had time to reach us in the 13.8 billion years since the Big Bang, has a radius of approximately 46.5 billion light-years. This number requires a moment of careful thought to understand properly, because it might seem contradictory. If the universe is 13.8 billion years old, how can we see objects that are now 46.5 billion light-years away? The answer lies in the expansion of space itself. The universe is not static, it is expanding, and the space between galaxies is stretching. When the light that we now receive from a very distant galaxy was emitted, the galaxy was much closer to us than it is today. As the light traveled toward us, the space through which it was traveling continued to expand, and by the time the light arrived, the galaxy that emitted it had moved much farther away. The 46.5 billion light-year radius of the observable universe therefore represents not the distance light has traveled, but the current distance to the most remote objects whose light has reached us, objects that were, at the time they emitted that light, much closer than they are now. The universe has expanded enormously since the earliest light we can detect was emitted, and this expansion is one of the central facts of modern cosmology, confirmed by multiple independent lines of evidence including the redshift of distant galaxies, the cosmic microwave background radiation, and the distribution of galaxy structures. The observable universe is itself just a sphere of a certain radius centered on the Earth, a horizon defined by the finite speed of light and the finite age of the cosmos. Beyond that horizon lies more universe. How much more, we do not and perhaps cannot know. Standard inflationary cosmology suggests that the total universe is vastly larger than the observable portion, perhaps infinite, depending on the global geometry of space. If the universe is spatially flat, as most current evidence suggests, and if the inflationary epoch was of sufficient duration, then the total universe may be incomprehensibly larger than what we can see. Some inflationary models suggest that the total universe contains approximately 10 to the power of 23 times as many galaxies as the observable portion, a number so large that it loses all meaning when stated as a quantity, and can only be contemplated as an expression of unbounded scale. Other models suggest the universe is literally infinite, extending forever in all directions, containing infinite galaxies, infinite stars, infinite planets, and if life arises wherever conditions permit, an infinite number of living worlds. This is either the most extraordinary possibility or the most dizzying one, and it sits at the heart of some of the deepest unresolved questions in modern physics and cosmology. The observable universe contains approximately 2 trillion galaxies, a figure that was dramatically revised upward from the previous estimate of 200 billion in 2016, when astronomers, using data from the Hubble Space Telescope and other observatories, made a careful accounting of galaxies too small and faint to have been previously detected. 2 trillion galaxies. Each galaxy containing, on average, perhaps 100 billion stars. This gives a total stellar count in the observable universe of approximately 200 sextillion stars, 2 followed by 23 zeros, or, as the number is sometimes expressed in popular science writing, more stars than there are grains of sand on all the beaches on Earth. This comparison has been checked and rechecked, and it holds. The number of grains of sand on all the beaches and deserts of our planet is estimated at approximately 7.5 times 10 to the power of 18, while the number of stars in the observable universe is estimated at approximately 2 times 10 to the power of 23, making the number of stars roughly 26,000 times larger than the number of sand grains. Every grain of sand on every beach represents not 1 star but 26,000 stars. And each of those stars may harbor planets. And each of those planets may harbor life. The question of life's prevalence in the universe is one that science has been building toward for centuries, and it is now, in the early decades of the 21st century, approaching the point where empirical answers may become possible. We know with certainty that life exists on one planet. We have strong evidence that the conditions necessary for life, liquid water, organic chemistry, energy gradients, are not rare in the cosmos. Water ice has been detected on the Moon, on Mars, on asteroids, on comets, on the moons of Jupiter and Saturn, in vast quantities in the cold molecular clouds of the interstellar medium. Organic molecules, amino acids, sugars, nucleobases, the chemical precursors of life, have been found in meteorites, in comets, in interstellar space. The conditions for chemistry are universal. What we do not yet know is whether the leap from chemistry to biology, from complex molecules to self-replicating systems, from replicating molecules to cells to organisms to minds, is a common outcome of those conditions or a rare and perhaps vanishingly unlikely event. The Fermi paradox names the tension between the apparent prevalence of suitable conditions for life in the universe and the complete absence, so far, of any confirmed evidence of intelligent life beyond our own world. If life is common, where is everyone? If technological civilizations arise, wherever conditions permit, why have none of them made themselves known to us? The paradox admits of many possible resolutions, some of them hopeful, and some of them deeply troubling. Life may be common but intelligent life rare, the product of an evolutionary accident unlikely to be repeated often. Technological civilizations may arise, but be intrinsically short-lived, destroying themselves through environmental collapse or conflict before they can make their presence known across interstellar distances. Interstellar communication may be vastly more difficult or energy expensive than we imagine, and civilizations may exist but simply not be making the kind of signals we are searching for. Or the universe may be so large, and civilizations so widely separated in space and time, that even in a cosmos teeming with life, the chance of 2 civilizations existing in detectable proximity to each other at the same epoch is small. Or, and this possibility sits most heavily on the mind, intelligent life may be extraordinarily rare, perhaps unique, and the silence of the cosmos may be telling us something about our own extraordinary improbability. We are, in this last scenario, not a common outcome of physical law but a remarkable accident, a singular and precious exception in a universe otherwise given over to the beauty of inanimate processes. The age of the universe, 13.8 billion years, was established through multiple converging lines of evidence. The rate of expansion of the universe, measured through the distances and recession velocities of distant galaxies. The age of the oldest stars in globular clusters, measured through stellar evolution models, the temperature and detailed structure of the cosmic microwave background radiation, the faint glow of heat left over from the era when the universe first became transparent to light. Approximately 380,000 years after the Big Bang. That moment, 380,000 years after the beginning, is the earliest we can see with light, because before that time the universe was so hot and dense that photons were continuously scattered by the plasma of electrons and protons that filled all of space, making the early universe opaque. The cosmic microwave background radiation, first detected accidentally by Otto Penzias and Robert Wilson in 1964 while they were testing a horn antenna at Bell Labs in New Jersey, and could not explain a persistent noise in their signal that turned out to be the afterglow of the Big Bang. This radiation fills the entire sky, reaching us from all directions equally, a nearly perfect thermal blackbody spectrum corresponding to a temperature of 2.725 degrees above absolute zero. It is the oldest light in the universe. When you look at the night sky and see darkness between the stars, that darkness is not truly empty. It is filled with the cosmic microwave background, photons from the earliest epoch of the universe, cooling and redshifting as the universe has expanded over 13.8 billion years. If you could see in microwave wavelengths, the entire sky would glow with this ancient light, warmer and brighter than any individual star, the echo of creation itself visible in every direction. Before 380,000 years after the Big Bang, we cannot see with light, but we can infer. The physics of the very early universe is described by the Standard Model of particle physics and by general relativity, and these theories allow us to calculate with confidence the conditions that prevailed at progressively earlier and earlier times. 1 second after the Big Bang, the universe was a sphere of plasma at a temperature of about 10 billion degrees, filled with protons, neutrons, electrons, neutrinos, and photons, all in thermal equilibrium and interacting furiously. In the first 3 minutes of cosmic history, as the universe expanded and cooled to about 1 billion degrees, nuclear reactions occurred throughout all of space, a process called Big Bang nucleosynthesis that produced the first atomic nuclei, hydrogen, helium, and traces of lithium. The ratio of these elements, approximately 75% hydrogen and 25% helium by mass, predicted by theory and confirmed by observation, is one of the most powerful pieces of evidence for our understanding of the universe's early history. It is a prediction that was made decades before the measurements to test it were possible, and the measurements, when they came, matched the prediction with a precision that still astonishes the scientists who work in this field. Going back further still, to times measured in microseconds and nanoseconds after the Big Bang, the physics becomes less certain, the theories less well tested, the territory more genuinely unknown. We know that at sufficiently early times, at energies accessible to the Large Hadron Collider and beyond, matter and antimatter were created in roughly equal amounts. We know that for reasons not fully understood, there was a slight asymmetry in the initial conditions, perhaps one extra particle of matter for every billion particles of antimatter, and that as the universe cooled and matter-antimatter pairs annihilated each other, this slight excess of matter was all that survived to become everything we see today. The galaxies, the stars, the planets, the oceans, the trees, the creatures, the thoughts, all of it is the surviving residue of that cosmological imbalance, that 1 in a billion asymmetry in the conditions of the universe at its birth. We are the flotsam of cosmic annihilation, the handful of matter that was left over when the great mutual destruction of matter and antimatter was complete. This is perhaps the most humbling genealogy imaginable, and at the same time the most extraordinary. That we exist at all is the consequence of a slight quantum wobble in the initial state of everything. Dark matter, the invisible, undetected, inferred substance that appears to make up approximately 27% of the total energy content of the universe, is among the most pressing unsolved problems in modern physics. We know it exists because its gravitational effects are unmistakable and reproducible. Galaxies rotate as though they contain far more mass than the visible stars and gas account for. Clusters of galaxies bend light in ways that require more mass than can be seen. The large-scale structure of the universe, the pattern of galaxy filaments and voids, cannot be reproduced in computer simulations unless a large quantity of non-luminous mass is added. The cosmic microwave background itself contains, encoded in its temperature fluctuations, the signature of dark matter's presence in the early universe. All of this evidence points consistently to the same conclusion. The universe contains roughly 5 times as much dark matter as ordinary matter. The Milky Way, for example, is believed to be embedded in a vast dark matter halo extending far beyond the visible disk of stars, perhaps 10 times larger in volume, providing the gravitational foundation within which the visible galaxy sits. What dark matter actually is, whether it consists of as yet undiscovered particles interacting through gravity and perhaps the weak nuclear force, or whether it reflects a fundamental modification of our understanding of gravity, or whether there is some more exotic explanation, remains unknown. Decades of experiments, from underground detectors attempting to catch the occasional interaction of a dark matter particle with atomic nuclei, to particle accelerator experiments searching for dark matter production, to astronomical surveys hunting for indirect signatures of dark matter annihilation, have so far yielded no definitive detection. Dark matter is simultaneously the best established and most mysterious component of the universe. Even more mysterious, and even more dominant, is dark energy, the name given to the cause of the observed accelerating expansion of the universe, the phenomenon for which Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011. In 1998, 2 independent teams studying the distances and recession velocities of type Ia supernovae, a type of stellar explosion that serves as a reliable, standard candle for measuring cosmological distances, made the same unexpected discovery. The universe is not merely expanding, but expanding at an accelerating rate. Distant supernovae are dimmer than they would be in a universe that was merely expanding at a constant rate or decelerating under gravity. They are farther away than expected, meaning that the expansion of space is speeding up over time. Something is pushing the universe apart. That something is called dark energy, and it constitutes approximately 68% of the total energy content of the universe. Its nature is profoundly uncertain. The simplest explanation is that dark energy is a property of space itself, a vacuum energy or cosmological constant, the energy of empty space. But the value of this vacuum energy predicted by quantum field theory is approximately 10 to the power of 120 times larger than the value inferred from cosmological observations, a discrepancy so enormous that it has been called the worst prediction in the history of physics. Other explanations invoke dynamical fields, modifications of gravity on cosmological scales, or entirely new physics yet to be discovered. We know dark energy is there. We do not know what it is. The ultimate fate of the universe, as best as current physics can project, is determined by the nature of dark energy. If the accelerating expansion continues indefinitely, the universe will undergo a slow dissipation. Galaxy clusters separating from each other, stars burning out over trillions of years, the last stellar remnants cooling to absolute zero across timescales of astronomical length. Black holes, the most durable objects in the universe, will eventually evaporate through Hawking radiation over timescales of 10 to the power of 67 to 10 to the power of 100 years for stellar mass and supermassive black holes respectively, periods so long that the current age of the universe is a negligible fraction of a fraction of a fraction of that time. After the last black hole has evaporated, the universe will consist of nothing but a thin, cold gas of elementary particles, photons, neutrinos, electrons and positrons in eternal equilibrium, expanding forever into a void of decreasing density and increasing darkness. This is the Big Freeze, sometimes called the heat death of the universe, the ultimate fate of maximum entropy toward which thermodynamics points with implacable logic. It is a scenario of surpassing strangeness, that a universe that began in a state of extreme heat and density should end in a state of extreme cold and emptiness, that the arrow of time should carry everything inexorably from the bright violence of the Big Bang to the silent darkness of the last cold photon. And yet the physics that describes this fate is the same physics that describes the motion of the planets, the chemistry of life, the patterns of thought in a human brain. The laws do not change at any scale. But the universe is not finished yet. Not by a very long way. We live not at the end of cosmic history but near its beginning, cosmologically speaking. The universe is 13.8 billion years old, and the era of star formation, the epoch when stars, like our sun, are burning and providing the energy for life as we know it, extends roughly from 100 million years after the Big Bang and is expected to continue for approximately 100 trillion years into the future, as the smallest, most fuel-efficient red dwarf stars slowly exhaust their hydrogen supplies. We are, in this perspective, early arrivals at a party that has barely begun. The generations of stars and planets, and potentially living worlds that will form in the next trillion years dwarf the population of the current universe in both number and duration. If life is common in the universe, the overwhelming majority of living worlds that will ever exist have not yet been born. The creatures, if there will be creatures, who will look up at their skies and wonder about the nature of reality in 10 billion years or 100 billion years, will be looking up at a universe that has changed beyond recognition. The accelerating expansion will by then have carried all other galaxies beyond the observable horizon. The night sky of a planet orbiting a red dwarf star in 1 trillion years will show nothing but the stars of its own galaxy, all the trillions of other galaxies hidden beyond an expanding horizon of darkness. The cosmic web, the large-scale structure we can map today, will have dissolved into isolated island universes, each galaxy cluster or group, perhaps just the merged Milky Way Andromeda remnant, isolated in the void, entirely cut off from the rest of the universe by the accelerating expansion of space. Those future observers will not know, from direct observation, that other galaxies ever existed. They will have to infer it from the physics of their stars, from the composition of their cosmic microwave background, from theoretical reasoning. They will be cosmologically blind in a way that we, living at this particular epoch when other galaxies are still visible, are not. In a sense, we are living in a uniquely privileged time to do cosmology, a time when the evidence for the universe's history and structure is still visible in the sky, before the expansion carries it beyond our reach. The cosmic microwave background contains in its temperature fluctuations a map of the density variations in the early universe, the seeds from which all the large-scale structure we see today grew under gravity over 13.8 billion years. These fluctuations are tiny, roughly 1 part in 100,000, meaning that the early universe was almost perfectly uniform, with only slight variations in density from place to place. The fact that these fluctuations have a specific statistical signature, a particular power spectrum, with characteristic peaks at angular scales corresponding to sound waves that propagated through the early universe's plasma, is predicted by inflation, The theory that the very early universe underwent a period of exponentially rapid expansion that stretched quantum scale fluctuations to cosmological scales. Inflation explains why the universe appears flat, why it appears homogeneous on the largest scales, and why the microwave background has the specific pattern of fluctuations that we observe. It is an extraordinary theoretical achievement, and its predictions have been confirmed with remarkable precision by successive generations of microwave background experiments. And yet inflation itself raises the deepest questions. What was inflating? What caused inflation to begin? What caused it to end? What happened before inflation? These questions probe the boundary of the known universe, the frontier where physics meets philosophy, where our equations run out and our ignorance begins. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to describe the physics of the Planck era, the first 10 to the power of negative 43 seconds after the Big Bang, when the universe was so dense and so hot that quantum effects and gravitational effects were both important, and a theory combining them is essential. These theories are mathematically elaborate and intellectually beautiful, but none of them has yet produced a testable prediction that has been confirmed by experiment. This is not a failure of science, but a consequence of the extreme conditions involved. The energies at which quantum gravity effects become important are 10 to the power of 15 times higher than those achievable by the largest particle accelerators we can build. We are trying to understand the physics of the beginning of time with instruments that can only reach a small fraction of the energies needed to directly probe it. It may be that indirect evidence, from the microwave background, from gravitational waves, from the large-scale structure of the universe, will eventually allow us to distinguish between competing theories of quantum gravity. Or it may be that the physics of the Planck era is fundamentally inaccessible to us, hidden behind a wall of physical law that our experiments cannot penetrate. We do not yet know which of these is true. Black holes deserve a longer consideration, because they are among the most extraordinary objects in the universe, and because they occupy a special place at the intersection of our deepest theories and our most dramatic observations. A black hole is a region of space where matter has been so compressed that the escape velocity, the speed required to escape the gravitational pull, exceeds the speed of light. Nothing, not even light, can escape from within the event horizon, the spherical surface that defines the boundary of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black hole at the center of the galaxy M87, the first black hole to be directly imaged by the Event Horizon Telescope in 2019, the mass is about 6.5 billion solar masses, and the event horizon has a radius of approximately 19 billion kilometers, larger than the entire solar system out to beyond Pluto. The conditions at the event horizon of a supermassive black hole are, counterintuitively, less extreme than at the event horizon of a stellar mass black hole. The tidal forces, which vary with the mass and size of the black hole, are mild enough that a person falling to the event horizon of M87* would not immediately notice anything dramatic. They would cross the point of no return without any local physical sensation of doing so. The singularity, where the density of matter and the curvature of space-time become mathematically infinite, lies ahead, not around them. It is only in retrospect, recognizing that light from the outside universe can no longer reach them, that the full horror of their situation would become apparent. Neutron stars are the remnants of massive stars that have exploded as supernovae, their cores compressed to densities at which atomic nuclei themselves are pressed together, creating a state of matter unlike anything on Earth. A neutron star typically has a mass of about 1.4 times the mass of the Sun, compressed into a sphere roughly 20 kilometers in diameter. At this density, A teaspoon of neutron star material would weigh approximately 10 million metric tons. The surface gravity of a neutron star is approximately 200 billion times the surface gravity of Earth. The interior of a neutron star, which we cannot observe directly, may contain exotic states of matter, degenerate neutron fluid, superfluids, superconductors, or perhaps quark-gluon plasma, a state of matter in which the quarks that normally make up protons and neutrons are freed from their confinement and flow freely. The most rapidly spinning neutron stars, called millisecond pulsars, rotate hundreds of times per second, their surfaces moving at an appreciable fraction of the speed of light. They emit beams of electromagnetic radiation from their magnetic poles that sweep across the sky like cosmic lighthouses, and where those beams happen to intersect the Earth, we detect them as pulses of radio waves arriving with extraordinary clock-like regularity, regular enough, in the case of the most stable pulsars, to rival the best atomic clocks on Earth as timekeeping instruments. The detection of gravitational waves in 2015 by the LIGO Observatory opened a new window on the universe, a new sense through which humanity, for the first time, could hear the cosmos rather than merely see it. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity and produced whenever massive objects accelerate asymmetrically. The first detected event, GW150914, was produced by the merger of two black holes approximately 1.3 billion light-years away, each black hole having a mass approximately 30 times the mass of the Sun. The merger lasted a fraction of a second and produced a brief burst of gravitational waves that, by the time they reached Earth, had distorted space by a fraction of the width of a proton, a compression and stretching of space smaller than any ruler could measure, detectable only through the extraordinary sensitivity of LIGO's 4-kilometer laser interferometer arms. In that fraction of a second, the merging black holes release more energy in gravitational waves than the combined luminosity of all the stars in the observable universe emit in light in the same interval of time. This is the scale of violence at which the universe operates when black holes collide, and the fact that we can detect it at all, across a billion light-years of empty space, through a signal smaller than a proton, is a testament to the extraordinary precision of human experimental technique. Gamma-ray bursts are the most energetic events in the universe after the Big Bang itself. Brief flashes of gamma radiation, lasting anywhere from milliseconds to several minutes, that for their duration outshine everything else in the observable universe. A long gamma-ray burst is believed to be produced by the death of an extremely massive star, a hypernova, in which the stellar core collapses directly to a black hole, and twin jets of plasma and radiation are launched at nearly the speed of light along the rotation axis of the dying star. In the first second of a long gamma-ray burst, more energy is released than the Sun will emit in its entire 10 billion-year lifetime. Short gamma-ray bursts, lasting less than 2 seconds, are produced by the merger of two neutron stars, or a neutron star and a black hole, events that also produce gravitational waves and a brief electromagnetic transit called a kilonova, in which heavy elements including gold, platinum, and uranium are synthesized through rapid neutron capture nucleosynthesis. The gold in a wedding ring, the platinum in a laboratory catalyst, the uranium in a nuclear reactor. These elements were formed in the catastrophic collisions of neutron stars, their atoms scattered across space, eventually incorporated into molecular clouds, condensed into new solar systems, accumulated in planetary bodies, and eventually, in at least one instance on at least one planet, worked by human hands into objects of ornament and utility. The heavy elements are carried from neutron star mergers to human hands across billions of years and billions of light-years of space. The formation of the first stars, approximately 200 to 400 million years after the Big Bang, ended what astronomers call the cosmic dark ages, a period after the cosmic microwave background was released but before the first luminous objects formed, during which the universe contained only hydrogen, helium, and darkness. The first stars, called population 3 stars, were very different from stars today. They formed from gas that contained no heavy elements, only hydrogen and helium, and because the absence of heavier elements meant that the gas could not cool as efficiently, these first stars were enormous, perhaps hundreds of times the mass of the Sun. They burned fiercely and briefly. The largest may have lived for only a few million years, and died in spectacular supernovae that seeded the surrounding gas with the first heavy elements ever created by stars: carbon, oxygen, silicon, iron. The remnants of those early stellar explosions enriched the next generation of gas clouds, enabling the formation of smaller, longer-lived stars and, eventually, after many generations of star formation and stellar death, the formation of planets with the chemical complexity necessary for life. We have not directly observed a population 3 star. We believe they have all died, their brief brilliant lives over long before the Earth formed. But the James Webb Space Telescope, launched in December 2021, is probing the epoch of their formation with unprecedented sensitivity, and we may in the coming years detect the signatures of these ancient stellar ancestors in the light of the very early universe. The James Webb Space Telescope is itself a marvel of engineering that represents the accumulated ingenuity of thousands of scientists and engineers across multiple nations over several decades of effort. Its primary mirror, 6.5 meters in diameter, is composed of 18 hexagonal gold-coated beryllium segments that unfold after launch and align themselves with nanometer precision. It observes in infrared wavelengths, allowing it to see through the dust that obscures much of the visible universe, and to detect the heavily redshifted light of the earliest galaxies. Positioned at the second Lagrange point of the Earth-Sun system, 1.5 million kilometers from Earth in the direction away from the Sun, it operates at temperatures below 50 Kelvin, the extreme cold necessary for its infrared detectors to function without being swamped by the telescope's own thermal emission. The first images released in July 2022 showed, in breathtaking detail, galaxy clusters, nebulae, and the most distant galaxies ever imaged, including objects from fewer than 500 million years after the Big Bang. These images were not merely beautiful, though they were that, abundantly and overwhelmingly. They were scientific data of incalculable value, the deepest views of the universe ever obtained, extending our observational reach to within a fraction of the cosmic dark ages themselves. The light in those images had been traveling for more than 13 billion years, crossing the entire width of the observable universe to fall on a mirror of gold and beryllium floating in the cold dark between Earth and Sun, focused to a point, converted to electrons, transmitted as data, reconstructed as color and form by human software, and displayed on screens for human eyes to see. It is one of the most extraordinary achievements in the history of our species. Exoplanets, planets orbiting stars other than our Sun, were once hypothetical. In 1992, the first confirmed detection of a planet beyond our solar system was announced. Planets orbiting a pulsar, a neutron star, discovered through the regular timing variations in the pulsar's radial pulses caused by the gravitational tug of orbiting companions. In 1995, the first exoplanet orbiting a Sun-like star, 51 Pegasi b, was detected through the radial velocity method, which measures the Doppler shift in the star's light caused by the gravitational pull of its orbiting companion. Since then, and especially since the launch of the Kepler Space Telescope in 2009, The number of known exoplanets has grown from a handful to more than 5,000 confirmed, with tens of thousands of candidates awaiting confirmation. The Kepler mission alone detected over 2,600 confirmed exoplanets by staring at a single field of approximately 150,000 stars and measuring the tiny dimming of starlight that occurs when a planet passes in front of its star. The statistical results from Kepler are perhaps even more significant than the individual discoveries. They tell us that planets are not rare exceptions but the norm, that the average star in the Milky Way harbors more than one planet, that rocky planets in the approximate size range of Earth are common, and that many of these rocky planets orbit in the habitable zones of their stars. The universe is, apparently, full of worlds. Whether any of those worlds are full of life is the question that none of our instruments can yet answer, but which the next generation of telescopes, larger, more sensitive, equipped with coronagraphs and spectrographs capable of analyzing the atmospheric chemistry of Earth-sized planets around nearby stars, is beginning to approach. The characterization of exoplanet atmospheres through transmission spectroscopy, observing the star's light as it filters through the planet's atmosphere during a transit and measuring how different wavelengths are absorbed by atmospheric gases, is one of the most exciting frontiers in contemporary astronomy. In 2022 and 2023, the James Webb Space Telescope provided the first definitive detections of carbon dioxide, sulfur dioxide, and water vapor in the atmospheres of transiting exoplanets, including the first detections of chemical weather processes and gas giant atmospheres. For rocky planets in habitable zones, the challenge is far greater. The signal is smaller, the background noise larger, and the number of transits observable in a reasonable time period fewer. But the tools are improving rapidly, and within the next decade or two, we may have spectra of Earth-sized planets in habitable zones around nearby M-dwarf stars, looking for the chemical signatures that we associate with biological processes on Earth: oxygen, ozone, methane, nitrous oxide. If we find such signatures on another world, it will be the most consequential scientific discovery in the history of our species. If we do not find them, if world after potentially habitable world turns out to be dead and lifeless under careful examination, that too will be a discovery of the deepest significance, raising again the question of why the universe is so quiet and whether we truly are alone in all this immensity. The possibility of intelligent life elsewhere in the universe has been the subject of formal scientific inquiry since the first SETI, Search for Extraterrestrial Intelligence, programs began in the 1960s. Frank Drake's famous equation, formulated in 1961 as an organizing framework for estimating the number of communicating civilizations in the Milky Way, multiplies together estimates of the rate of star formation, the fraction of stars with planets, the fraction of planets where life arises, the fraction of life-bearing worlds where intelligence evolves, the fraction of intelligent species that develop detectable technology, and the average lifetime of such civilizations. The product of all these terms is the number n, the number of communicating civilizations in the galaxy at any given time. Early optimistic estimates of Drake's equation suggested that n might be in the millions. More sober assessments, taking into account the apparent rarity of complex multicellular life in Earth's history and the many potential filters that might prevent technological civilizations from arising or persisting, suggest n might be much smaller, perhaps just a few, perhaps just one, perhaps zero other than ourselves. We have been listening for radio and optical signals from other civilizations for over 60 years now, with steadily increasing sensitivity and sky coverage, and we have detected no unambiguous signal of artificial origin. This negative result is itself data, constraining the possible values of the Drake equation's terms, though the interpretation of this null result remains deeply contested. The universe is simultaneously the source and the subject of our longest meditation. Since the first hominid looked up at the night sky with a brain capable of registering not just the brightness of the stars, but their pattern, their constancy, their mystery, we have been conducting an inquiry that has no precedent in the natural world. No other creature on this planet, as far as we know, lies on its back in the darkness and considers the distance to the nearest galaxy. No other creature builds instruments to measure the redshift of light from objects 10 billion light-years away. No other creature has deciphered the light of dead stars into a table of elements, has found in the spectral lines of distant suns the same calcium and sodium and iron that make up its own bones and blood. This capacity for cosmological consciousness is perhaps the strangest and most remarkable thing about us. We are made of the same atoms as everything else in the universe, assembled by the same physical processes, subject to the same laws, and yet we alone, or so we believe, or suspect, or hope, have become aware of all this. We are the universe looking at itself. Not with perfect eyes, not with complete understanding, but with genuine effort and genuine humility and genuine wonder. The scale of the cosmos has a moral weight as well as a scientific one. When Carl Sagan described the Earth as a pale blue dot, a description prompted by the photograph taken by Voyager 1 in 1990, turned back to photograph the solar system from a distance of 6 billion kilometers and showing the Earth as a fraction of a single pixel, suspended in a band of scattered sunlight. He was making not just an observational statement, but a philosophical one. That tiny mote of light contains everything we have ever known or loved, every act of heroism and cruelty, every moment of joy and grief, every civilization and every wilderness, every creature that has ever drawn breath. The scale of the cosmos does not diminish this. On the contrary, it clarifies it. When we understand how rare, how fragile, how improbable is the thin film of life on the surface of this particular rock, the moral weight of our choices here becomes not lighter, but heavier. Every decision we make about how to treat each other, how to treat the other creatures with whom we share this planet, how to protect or destroy the systems that sustain life, these decisions matter more, not less, when placed against the backdrop of cosmic emptiness. We have not found another world where love exists, where music is made, where children are born and taught and grow into people capable of understanding the structure of the atoms in their own hands. Until we find such a world, we are holding something singular and irreplaceable. The sun will continue to burn for approximately 5 billion more years, though in about 1 billion years it will have become bright enough that the oceans of Earth will begin to evaporate, gradually destroying the conditions that support life. In about 5 billion years, the sun will expand into a red giant, its outer layers swelling to perhaps 100 times their current radius, likely engulfing Mercury and Venus and possibly the Earth. After the red giant phase, the outer layers will be expelled as a planetary nebula, a shell of glowing gas surrounding the cooling white dwarf that the sun's core will have become. That white dwarf will cool over billions of years to a black dwarf, a dark and inert remnant of the star that once lit our world. None of this, it should be said, is a calamity in cosmic terms. It is the ordinary life cycle of a star, repeated trillions of times throughout the universe. The materials of our solar system will be recycled. The planetary nebula of the future sun will enrich the surrounding interstellar medium with carbon and oxygen, contributing to the next generation of stars and planets. Nothing is wasted. Everything continues in different form. What can we say, after traveling so far together in the mind, about the true scale of the cosmos? We can say that it is incomprehensibly large, that our instruments have extended our sight to distances of 46 billion light-years and found no edge, no boundary, no wall at which the universe ends. We can say that it is incomprehensibly old, that the universe has been evolving and complexifying and building structures for 13.8 billion years, and will continue to do so for trillions more. We can say that it is fecund, full of stars and planets and chemistry and energy gradients, the raw materials from which, on at least one world, life has assembled itself and eventually looked back at the cosmos with wondering eyes. We can say that we do not know how much of the cosmos harbors life, that this is one of the great open questions of our time, and that we are building the instruments to begin to answer it. We can say that the laws of physics appear to be uniform throughout the observable universe, that the same equations that describe the motion of a thrown stone describe the motion of a galaxy, and that this uniformity is itself a deep and beautiful mystery. We can say that there is much we do not understand: dark matter, dark energy, the nature of quantum gravity, the origin of the initial conditions of the universe, the question of whether our universe is unique or one of many, and that this ignorance is not a reason for despair but a landscape of opportunity, a territory of unknowing waiting to be explored. The night sky, seen from a truly dark place far from the pollution of city lights, is an overwhelming sight. The band of the Milky Way arches overhead, a river of light composed of hundreds of billions of individual stars too distant to resolve, their collective glow forming a luminous stripe across the darkness. Scattered across the sky are the points of light we call stars, each one a sun, many of them many times larger and hotter and more luminous than our own, some of them so distant that the light now entering your eye left them when your grandparents' were children, or when Roman legions were marching across Europe, or when the pyramids were newly built, or when the last ice age was beginning to end and human beings were painting animals on cave walls by firelight. The planets, brighter and steadier than the stars, trace their ancient paths across the ecliptic, their positions shifting night by night and year by year, the visible evidence of the clockwork of gravity that Kepler described and Newton explained and Einstein refined. In the southern sky, a smudge of light marks the large Magellanic Cloud, a satellite galaxy of the Milky Way, 160,000 light-years away. In the northeast on autumn evenings, the Andromeda galaxy floats above the horizon, 2.5 million years of light travel separating it from your retina. Every photon striking your eye has crossed a distance that took it, traveling at the fastest speed in the universe, longer than the entire history of our genus.